My name is Jonathan Magan, and this is going to be Project 2, Part 3, Airflow over an airfoil. Originally, this project was designed so that we would put the airfoil in the test section we created in Project 1. However, we are typically allowed to put it in any domain as long as the velocity is equivalent to the test velocity at 30 hertz, correlating to the power of the fan at the end of the diffuser. So just like the previous video, I'm going to quickly go over how to import the airfoil coordinates and then put them into the geometry of Fluent. So first and foremost, I'm going to quickly go to the internet. Where are we at here? Airfoil tools. You're going to go to airfoiltools.com, and in the top right search bar, for this specific part of the project, we're going to use NACA 2412, which is a cambered airfoil. You can just click the search button up here, then go to, scroll past the ads and click on this one here. And once you pop this up, it's going to give you a two-dimensional shape of the airfoil. And here in the DAT file, you can actually see the X and Y coordinates that you're going to need for the project. And if you scroll down to the bottom, you can also see the lift coefficient versus angle of attack graphs, the drag coefficient versus angle of attack, and things like that, which will be helpful for the analysis portion of this project. But in order to import our files, you're just going to copy all of these files here. And I'm actually going to share my full screen again. And you're going to actually go over to, let me minimize these tabs here. You're going to create a text file. So you're going to right click on the home screen, click new, and then click text file. And basically you're just going to copy and paste your XY coordinates into here. Now, once you get them into your text file, I'm actually going to show you really quickly the text files that I already have. Project 2, NACA 2412. So these are our coordinates. Now, I've already scaled these coordinates properly. They give you a chord length of 1 in the airfoil database. However, you need to scale it up by 5 to have a chord length of 5 inches. So in order to do that, again, you'll copy and paste this data into a Excel document. So we'll let that load up. Over here, you see the previous version where the chord length is 1, and this is the scaled version. The first column is necessary to have all 1s. The second column is allocates each coordinate point to a number. So here we have 81 coordinate points. And the right here, we have our X coordinate. Here we have our Y coordinate, and we're going to put zeros along our Z coordinate because we're only using 2 dimensions. In order to scale everything up by 5 in Excel, you can just put your scaling factor in a random box, and you can just use the code up here, which is where you set your initial value that you want to scale, and you multiply it by your scaling factor, and then you can just basically click and drag down the column. So once you're completed this, you want to copy and paste all of the new data here. Let me undo this really quick. Let me just exit out of that. Do not save. You want to copy and paste your new scale data and again put it back into the coordinates. And then once you go into Fluent again, I'm going to go back to this design module. You're going to go to this, you're going to go to concept, you're going to go to 3D curve. Once you get the 3D curve up, you're going to, actually, my apologies, you're going to go to point first, which is right here. And then you're going to upload your coordinates from the text file. And once it does that, when we zoom in here, you can see that our points are already connected, but essentially this is what it would look like. You just have these points everywhere. Following that, you want to do a 3D curve. So you go to concept, 3D curve, and then you can do point selection. And once this is done, essentially this is going to connect all your points together, except the last trailing points here. As you can see here, it is empty. But because we have another tool here called concept and then lines from points, and these lines from points, line 2, this will allow us to connect the trailing edge just so we can have a complete shape. After this, it gets a little bit more tricky. We have to create a surface specifically over our airfoil. Again, that's concept, surfaces from sketches, and that'll complete that. Actually, my apologies. You go to concept, you go to surfaces from edges, then you click the edge of the airfoil, and then click generate, and that will create your surface for your airfoil. After that, you want to create a surface of the domain, which is again from concept, and then surface from sketches. After this, we need to use a Boolean and subtract the two surface areas from each other in order to have that clear area that we see in there. And to do that, you just go to create, and then you go down to Boolean, and then you want to make sure you're on the subtract operation, and your target body should be the domain that your airfoil is in, and your total body should be the airfoil itself, the airfoil surface. And once you click generate, you will have this surface that you have here. So it's a little bit of a complicated process, but again, it works just fine. So after this, we're going to go to our meshing. Meshing's a little bit more straightforward, just like before. We're going to right click on mesh, go to insert, and we're going to click method. And this will give us the automatic method, which will put a general mesh over everything. So for our automatic method, I decided to use quadrilateral dominant because I figured this would be appropriate. You can also use the triangle method as well. Either or will work as long as it will converge in the setup portion. In order to make this a more refined mesh, we can go to 0.003 element size. This is already a very small object as it is, so we can't go too much smaller with the computer starting to crash. So I'm not going to do a refinement. I'll leave it as it is. For our name selections, we have the airfoil itself, which I labeled here. We have our velocity inlet, our pressure outlet, and our symmetry, meaning that velocity, this is not going to be treated as a wall. It's just going to be treated as the entire domain. And once you have this complete, then you're allowed to move on to the setup portion, which I will show here. I've gone and performed the calculation already, just to speed things up a little bit. But essentially, for this, you're going to use a standard K epsilon viscous model. For the boundary conditions, because we were simulating the 30 hertz velocity of the test section, we're going to have a velocity of, I believe it is approximately 7.29, we'll see in a second, 7.0952. And again, that's the velocity of the test section that we would have if this airfoil was actually in the test section. We want to make sure our symmetry is just labeled as symmetry. Our outlet is pressure outlet, and that should be good for boundary conditions. For the reference values, we have to make sure we calculate from our inlet and that our velocity changes to what we had in our boundary conditions. We then go to initialization, hybrid initialization, initialize. And then we can run our calculation, making sure we go up to 500 iterations to make sure that our solution actually does converge. Thankfully, our mesh is very small, so it converges very fast. After this, once the calculation is complete, we are able to actually get our lift coefficient and drag coefficient, and that can be done through the report definitions. Now, normally you can do a calculation for the lift coefficient. However, I found it easier just to go through Fluent because it gives you a nice layout of, again, of the lift coefficient. So you click on report definitions, go to new, you're going to go to force report, and then you're going to go to lift. You're going to make sure you're in the Y vector direction, making sure that is 1. You're going to click the wall surface body, which is the airfoil itself. You're going to click report plot and compute. Clicking exit out of here, closing that. If we go to our console and drag that up here, minimize everything else here, you'll see that our lift coefficient is 0.0232. And your lift coefficient at 0 angles of attack is actually going to be a little bit greater than that of the symmetric airfoil, NACA 0012, because, again, you have that camber, which is going to cause a slight pressure difference, which is going to give you a little bit of lift. So in order to calculate our drag coefficient, we're going to do the exact same thing. You're going to go to report definitions, go to new, force report, drag coefficient, making sure the drag is obviously going to be in the X direction, so make sure our force vector is in the X direction. Click report plot and compute. And if we look over here, our drag coefficient is 0.003. And we have a pretty streamlined body. It's not too blunt, so we're not going to really have too much drag, as opposed to like having a cylinder or another blunt body. And once this is complete, we actually need to do a plot of the pressure coefficient distribution across the airfoil surface. In order to do that, we can go to plots, go to XY plot. We can just rename that as CP distribution, just like that. Then we can highlight, actually, no, we're not highlighting everything. We just want to do our wall surface body. And then we're going to go down to pressure and then change static pressure to pressure coefficient, making sure, again, our plot direction is 1. And then we're going to click Save and Plot. We'll click Close, and we're going to bring our graphics back up just like this. Now, this is along the direction vector, so if we want to change that to the curve length, we'll do that really quickly, making sure it's wall surface body, just like this. So as you can see, our CP varies between a maximum of approximately 1, which is what we would expect, and it kind of dips down to about negative 0.045 approximately, just through this, maybe negative 0.05. But again, this is what we're expecting for our pressure coefficient along the outside. We're going to have a maximum pressure coefficient at the leading edge and a minimum at the trailing edge. And that's just due to the way static pressure is distributed. Once this is complete, we can minimize this and go to our final section, which is doing our contours. So up here, we see we have our velocity streamline. I did 50 streamlines, I believe, along here, just so you're able to actually visually see the streamlines. If you put too many streamlines, you won't be able to see the details. I'll show you how to make that plot momentarily. Next, we have our velocity contour. Again, seeing our maximum velocity occur over the upper edge of our airfoil. Let me minimize that. Next, we have our turbulent kinetic energy. Our kinetic energy is going to be greatest along the exterior of our airfoil, just because that is the energized boundary layer. Next, we have our static pressure contour. Again, static pressure kind of relates to the pressure coefficient. We're going to have a minimum pressure coefficient at the top of the airfoil and a maximum at the front leading edge of the airfoil. Now, in order to create these contours, just like before, you're going to click the contour button up here. You're going to name your contour appropriately. And then you're going to just make sure your locations are at symmetry 2. Change your variable and make sure your contours are between 100 and 200, and that will just allow for a smoother contour. In order to get the streamlines, you can actually just click the streamline button up here. Rename it to velocity streamlines. And then down here, you want to make sure this is on all domains. You want to calculate from the inlet. And I did about 70 points on this one. Again, I believe I said something different earlier, but 70 is what I chose for this one. And as you can see, 70 gives a perfect demonstration of the streamlines and what's going on around this airfoil. And as we said, this is a streamlined body, so we have a little bit of flow separation up here, but nothing too concerning. So that is going to complete the part 3 of project 2. My partner, again, will be completing part 2 of the project, and that will be uploaded separately on a different channel. Please look in the project report for the YouTube links. Thank you so much for watching.